Now let us see how to represent the deadlock. Now assume that the system has finite number of resources and each of the resources are grouped into various types of resources. Assume that every resource type can have n number of identical resources called as instances. What is this? We will see. Now, in order to describe a deadlock, we can make use of graphical representation. As we have seen, what is a graph? A graph is nothing but a set of vertices and edges. A graph is nothing but which contains set of vertices and set of edges. Now, inside this vertices, we have another two subdivisions. That is, one is set of vertices which contains process and set of resource types. Now, this process is represented using circular fashion, and resources are considered or represented using rectangle, and as I have told you, each resource type has n number of identical resources. So, n number of identical resources represented using dots. N number of identical resources, that is called as instances. That is, for example, here I have 3 instances. That is, 3 identical resources are there for this particular resource. I repeat, process is represented using circle, resource type is represented using rectangle, and the instances of each resource is represented using dot present inside the rectangle. Next, I have edges. With respect to edges, I can have 2 types of edges. One is request edge, another one is allocation edge or assignment edge. Request edge. What is this request edge? Whenever a process, as you can see here, whenever a process is going to request for a resource, that is process PI here. Process PI is requesting for the resource RJ, then it is called as a request edge. I am going to represent it like this. PI requesting for resource RJ. Next, in this resource RJ, it has 2 instances. 2 dots represents 2 instances. Now, after the request is being given by process PI, the operating system should see to that whether it can allocate the request to the process PI. When it is trying to allocate or give the instance of RJ resource, it is going to tell that RJ can be provided for PI with the help of allocation edge. That is, resource RJ is allocated to PI, or instance of RJ resource is allocated to process PI. That is, from your dot, you are going to write the assignment edge or your allocation edge, telling that this one instance, there are 2 instances in this particular example, one instance of resource RJ is allocated to process PI. One instance of RJ is allocated to process PI. This is what is called as your allocation edge or assignment edge. Please observe here. Here you are trying to ask the request. After requesting, it is being assigned. Please check the difference here, how to write the arrow marks. So this type of representation is called as resource allocation graph. That is what I have written here. Resource allocation graph is nothing but a graph that consists of set of vertices, that is V, and set of edges E. The set of vertices V is partitioned into 2 different types of nodes. One is process P, that is your resource vertices edge, that is P, which consists of n number of processes P1, P2, Pn, which are all active processes. They are active processes, remember. Next, resources are R1, R2 up to Rm, which are nothing but a set of resources types in the system, the set of resources present inside the system. Now we shall see how to write the resource allocation graph. How to write the resource allocation graph. Now, as you can see here, the set PRE. P is nothing but set of processes, R is nothing but set of resources, E is nothing but set of edges. What is this? We will see. It tells that P1, P is a set of processes which contains P1, P2, P3. R is a set of resources which contains R1, R2, R3 and R4. Now, what is this edges? We will see it later. Next, resource instances. What is the resource instances? The set is having three processes, that is process P1, process P1, process P2, process P3. Next, resources. There are four resources: resource R1, resource R2, resource R3 and resource R4. Now it is telling that resource instances, one instance of resource type R1. Only one instance is there. I have already written here. Only one instance of resource R1 is there. Next, two instances of resource R2. Two instances of resource R2. Next, again one instance of resource R1. One instance of resource R3 and four instances of resource R4. Three instances of resource R4. Okay, four instances of resource R4. Four instances of resource R4. Now, process states. Process states, it tells that process P1 is holding instance of resource R2. Process P1 is holding instance of resource R2. Resource R2. That is, process P1 is holding the instance of resource R2. It is holding the instance of resource R2 and waiting for resource R1. Waiting for resource R1. Next, process P2 is holding the instance, please observe, process P2 is holding the instance of resource R1 and is waiting for resource R3 and is waiting for resource R3 and is waiting for resource R3. Waiting for resource R3. Next, process P3 is holding the instance of resource R3. Process P3 is holding the instance of resource R3. Now, what happens if you see in this allocation graph? Now, for P1 to complete, for P1 to complete, for process P1 to complete, it requires resources R1 and resource R2. Next, for process P2 to complete, it requires resource R1, resource R2 and resource R3. Next, for process P3 to complete, it requires resource R3. It requires resource R3. Now what happens? Once the process P3 completes its execution, it is going to release. It is going to release the resource R3, and once the resource R3 is released, it is being given to process P2, and since process P2 is already having R1 and R2 in it, it will acquire even your R3 process, R3 resource, and it will complete its execution. After completing the execution of P2, it is going to release the resource R1, which is required for process P1 to execute. Once the R1 is released, once R1 is released by process P2. Even process P1 can complete its execution with R1 and R2. So this is the example of your resource allocation graph. Now say suppose here if we have the request like this, if we have the request like this, that is, if process P3 wants the resource R3 as well as resource R2 to execute. If process P3 wants resource R3 and R2 to execute, then deadlock will occur. Then the deadlock will occur. That is, now if you see here, process P3 wants resources R3, R2. Process P2 wants R1, R2, R3. Process P1 wants R1 and R2. Now here if you see here, P3 wants R3 and R2, but R2 is having only 2 instances, and these 2 instances have already been allocated to process P1 and P2. Process P1 and P2. And here if I see here, in order to release these resources by your P1 and P2, in order to release these resources, process P2 also wants resource R3, which is being held by process P3. In turn, process P3 cannot complete its execution because it is not having R2 with it. So here if I come, P2 cannot do because R3 is not there, and here P1 cannot execute because R1 is not there. So such condition is called as a deadlock situation. There is a cycle as well as deadlock can occur. Now how to find the cycle? How to find the cycle? Here if you observe here, P1, from P1, process P1 is requesting resource R1. R1 is allocated to P2. R1 is allocated to P2, and P2 is in turn waiting for resource R3, process P3. P3 is waiting for resource R2. R2 is being allocated to process P1. I repeat once again. If you see here, process P1 is requesting for R1. This R1 in turn is allocated to process P2, but process P2 is waiting for resource R3. Process P2 is waiting for resource R3, and resource R3 is allocated to process P3. R3 is allocated to process P3, and P3 is in turn waiting for resource R2. In turn waiting for resource R2, but R2 is allocated to P1. R2 is allocated to P1. That is, P1, from P1 R1, R1 to process P2, from P2 to R3, from R3 to process P3, again from process P3 you are going to have this one particular cycle here, this one particular cycle. Then one more cycle also can occur. What is this one more cycle which can occur is that if you check or start from process P2, I am going to write the cycle here. From P2 is requesting R3. P2 is requesting R3, but R3 is in turn allocated to process P3, and P3 is in turn allocated to waiting for R2, and R2 is allocated to process P2. Here if you see, process P2 is requesting for resource R3. R3 is allocated to process P3. P3 is waiting for R2, but R2 is allocated to process P2. From process P3 again you can have a cycle 2, cycle 1. So this is an example for resource allocation graph with cycle wherein deadlock will occur. Now, even though we have cycle, there is a possibility for deadlock not to occur. That is, as you can see here, process P1, there are 4 processes P1, P2, P3 and P4 and 2 resources R1 and R2 with 2 instances respectively. Here if you check, here process P1 is requesting for resource R1, but R1 is being allocated by process P2 one instance and another one instance is allocated to process P3, and in turn process P3 is requesting for resource R2, wherein R2, one instance of R2 is allocated to process P1, another one instance is allocated to process P4, Now if we check the cycle, I can see here starting from process P1 is requesting for resource R1, but here if you see, R1 is allocated to 2 resources P2. If I take P2, it will not form a cycle. If I take P3 here, P3, in turn P3 is waiting for resource R2, but resource R2 is having 2 instances, one is allocated to P1, another one is allocated to P2. So process P1, it forms a cycle, but never it is a deadlock. It is not a deadlock. Why? Because here if you see here, if process P4 to complete, it wants only one resource. After completing this resource, it is going to release R2 and R2 can be given for process P3. Why? Because process P3 wants R1 and R2 to execute. Next, if I see process P2, only R1. Next, for process P1 to execute, it wants R1 and R2. Already process P4 is having or holding your R2 resource. After completing, it can release this resource. P3, it is holding R1 and waiting for R2. Once R2 is released by P4, it can complete its execution. Next, if I see here process P2, only one resource is required, that is R1. And since there are only 2 instances, after the completion of process P2, it can release this resource and P1 can complete its execution with the help of R1 and R2, because R2 is already given to P2. It is holding R2 and waiting for resource R1. So even though I have cycle, I repeat, even though I have cycle here, it is not going to form deadlock. This is an example for resource allocation graph with cycle, that is cycle 1 and cycle 2, 2 cycles with cycle which forms deadlock. This is an example with no deadlock. Even though I have cycle is there, but it does not form deadlock. We shall see the various strategies used for deadlock situation. What are these various strategies? Various strategies are deadlock prevention, deadlock avoidance, deadlock detection. I repeat, deadlock prevention, deadlock avoidance, deadlock detection. What is this? We will see. Inside your deadlock avoidance, you have an algorithm to be studied which is called as Banker's algorithm. Now I am telling that we will be discussing about the deadlock prevention. As you are aware now, a deadlock to occur, there are 4 necessary conditions. First one is mutual exclusion, second one is hold and wait, third one is no preemption, Last one is circular weight condition. 4 conditions to be met. In order to see deadlock prevention, all the 4 conditions should be met. That is your mutual exclusion, next hold and wait, next no preemption, and last one is circular weight condition. Now, first is your mutual exclusion condition. How does your mutual exclusion condition look? Assume that you have as we know that mutual exclusion is nothing but a non-shareable resources. Deadlock prevention, as we have seen, the first condition is your mutual exclusion. So in this mutual exclusion, say suppose you have a printer in your system. Say suppose you have a printer in your system. A printer cannot be simultaneously used by more than one process. That is, it is a non-shareable resource. It is a non-shareable resource. Your printer is a non-shareable resource wherein a printer cannot be simultaneously shared by several processes. So, since it is a non-shareable resource, it will not accept your mutual exclusion, or we cannot break the mutual exclusion concept. Next, if I see here, we'll check other conditions, that is your hold and wait condition. If I see hold and wait condition, here if I see here, say suppose a process can request for a resource if it has none of the resources in it. I repeat, a process can request for a resource if it has none of the resources in it. And this restriction, if such restriction is put, then hold and wait condition can be broken. That is, as you have seen earlier, process P1 was holding resource A and then waiting for resource B. Such conditions should be removed, or such restriction should be removed, so that each process, whenever it wants to request a resource, it should request only if it is not having any of the resources in it. In such conditions also, we can remove the hold and wait condition. Next, no preemption. This condition can be broken when process PI is going to request resource RJ, when process PI is going to request resource RJ, but this RJ is being allocated to process PJ, then it leads to deadlock. So what we can do is, if process PI is holding a resource, assume that it is holding a resource Ri and waiting for Rj, then what we can do, we can ask this process Pi to release this resource, add this resource into the system, and then ask process Pj to release the resource Rj after the execution is completed. Or forcibly, here we are trying to tell process Pi to release the resource Ri which is being held by process Pi. Now also we are trying to break this preemption, because we are trying to force Pi to release the resource Ri. Next, since circular wait is an extension of hold and wait, here since we can break hold and wait conditions, even circular wait condition can be broken. How is that? Here we can tell that we can define one-to-one function. That is, f is a function which has a set of resources, wherein set of resources is nothing but, previously we have seen, R2, R3 up to Rm is nothing but a set of resources. which has n number of integers, natural numbers. And these resources can be your tape drivers, it can be disk drivers and printers. Now, say suppose I have defined a function f wherein r has n number of integers, resources has n number of integers. We can now consider the following protocol to prevent deadlock. How to prevent deadlock is that each process can request resources only in the increasing order, That is, as I told, resources are all these three types. Increasing order, that is function f of tape driver equal to 1, f of disk driver equal to 5, and f of printer equal to 12. Now it can ask or it can request the resource, only in increasing order, increasing order of enumeration. That is, a process can initially request any number of instances of a resource type, and only if f of rj is greater than f of ri, only if f of rj is greater than f of ri, this condition should be met. When these conditions are met, we can prevent deadlock. So all these four conditions are necessary to tell that a deadlock is occurred. If in case any of these conditions fail, then we can tell that deadlock cannot occur. So in this example we have seen we cannot break your mutual exclusion because printer is a non-shareable resource. Then next, hold and wait can be broken. No preemption can also be broken. Circular wait can also be broken. Since these three conditions are not satisfied, we can prevent deadlock. This is the explanation for your deadlock prevention. In the next video, we shall see how to avoid deadlock using Banker's algorithm. Thank you.